Okay, thank you everyone for being here today. This presentation is part of the Center Project Final webinar series focusing on transforming household energy for a smarter and greener future. Today's webinar concerns smart grids, interoperability in the IoT solutions towards unlocking the power of demand response. The presentation will approximately last about 1 hour and a half, and the sections that will be addressed initially will be the identified consumer segments in demand response and energy monitoring and adoption. Then we will jump to the how to address the question how sender enhanced the grid flexibility, and more specifically, we will focus on the project scope as reflected in the sender's use case. We provide an interoperable architecture report that was implemented to realize these use cases. Then we will go over the flexibility provision services that were delivered within Sender, and we will make a part. We will dedicate a part in the validation and testing of the respective solution in the simulated environment. Then we will focus on the technological breakthrough of the Sender Smart Kit and the more hardware-based solutions from the hardware point of view of the solutions. And finally, we have dedicated smaller section on the data management, security in the smart energy systems, which is very crucial for today's information exchange. Now, regarding the identified consumer segments, a survey was performed both in Spain and the United Kingdom with over 1,000 participants in each case. And these are the segments that were identified, beginning with the homeowners and renters. Of course, the homeowners are very more likely to invest in long-term energy efficient solutions as they are owners of their homes. But contrary to renters, which may be reluctant due, of course, to lack of control over their home infrastructure. In larger households, the owners are relatively more interested, and they show a higher adoption rate due to higher energy consumption of the premises. So this type of consumer segment tends to be more responsive to demand response programs, and if the savings are substantial. Then, of course, within those households, there are older people, elders, that generally are more focused on the functional benefits of the solutions, like the convenience, the comfort, and usability. And of course, they are less likely to prioritize any technical features or participate in demand response schemes. Then, another segment identified was the tech-savvy and the younger consumers, which are more inclined to use all the mobile apps and the energy management systems, and ultimately participate in the demand response schemes. Also, financially motivated consumers, primarily interested in the financial savings appeared on their electricity bills. We have also the innovative consumers, which are generally more open to adopting new energy technologies and services and experiment with demand response schemes and the overall energy monitoring apps. And finally, the environmentally cautious consumers, motivated by reducing the greenhouse gas emissions and all the overall sustainability benefits. Now, let's jump to the first section of the webinar to address the question how Sender enhance grid flexibility. So, to deliver an overview of the Sender's technological objectives, the expected results most commonly were related to, first of all, the development of a next generation energy service application, which focuses on demand response, home automation, convenience in a secure manner. To be able to do so, we needed to capture the consumption and also remote control different residential loads, such as HVAC systems, domestic hot waters, EVs, renewable systems, etc. as soon as we captured this information and able to dispatch these control commands, we needed to integrate different systems, capturing different appliances in its household in order to have an interoperable solution from different technological data provision solutions. Furthermore, in parallel, we wish to improve the load forecasting, analyze behavioral patterns, and eventually maximize the extracted flexibility through the usage of state-of-the-art machine learning algorithms. This overall focus also aims to empower the grid stability indirectly by applying remote load shifting and making available day-ahead baselines in order to be provided to grid operators and DSOs. Lastly, as mentioned earlier in the consumer segments, we wish to actively engage household participants in demand response schemes through interactive mobile apps with a focus on raising the overall user awareness. And how we implemented the steps to realize the technological objectives. First of all, we had to draft the project and user requirements. And based on these project and user requirements, to design the specifications of the different modules. And after this process was finalized, we needed to design and deliver a system architecture that would showcase the overall data acquisition flow, interactions among sender solutions and components. And as soon as the defined architecture, the architecture has been defined, we needed to jump to the development of the components and, of course, testing and fine-tuning in simulated environments with the sole focus of the sole purpose to demonstrate the solution in real-life building cases in a mass deployment scheme. Okay, regarding now the load types that were captured and the overall household reach achieved, the main loads that were monitored and controlled were the total consumption, first of all, and of course the respective submetering of HVAC devices and DHW devices. We captured the generation of photovoltaic systems, the EV chargers as well, and of course we gathered ambient condition from the households regarding the air temperature, the relative humidity, illuminance, and occupancy. The total reach in which there were finally deployed the devices reached at about 236 households in 3 different countries, Spain, Finland, and Austria, providing a diverse climate region around Europe to test the solutions. The vast majority of the households were detached and semi-detached houses at the rate of over 8%. 14% of the households were apartments, and a very small percentage, under 2%, corresponded to multifamily houses. There were very different available loads from the participants, PVs for some consumption, EVs charged at homes, heat pump for HVACs, boilers, smart boilers, distant heating related appliances, underfloor heatings, other heating appliances with resistive loads such as radiators and stuff like that, solar system with contributions to space heating, and a small portion of heat pumps that work with ground source. Now, the overall sender scope was expressed through 4 distinct use cases. And beginning with the first, maybe the most important use case was the residential explicit demand response. This use case described how the sender solution would extract flexibility from different assets of a smart home and propose, of course, the flexibility to an interested market. The second use case concerned the maximization of the renewable energy sources usage by loading shifts to preferable time slots from a PV generation point of view. And in parallel, the use case 3 perform similar, described a similar task, but instead of focusing on PV generation preferable time slots, we focused on tariffs, tariff prices, excuse me, that were preferable for the consumer. Finally, the last use case would correspond to the monitor and control of home devices remotely. You know that this use case is closely related for the realization of the previous use cases. And of course, it was part of the sole purpose of the project to raise awareness of the users and trigger them to participate in adopting energy, either participating in their response schemes or simply adopting energy monitoring solutions. Now, this is a high-level depiction of the center architecture, segmented in basically 3 layers. The bottom layer is the device layer, which includes all the IoT devices and smart equipment overall that was deployed in order to capture the several metrics concerning the energy consumption, indoor ambient condition, and of course, dispatching of remote control commands. In order to communicate in a homogeneous way with diverse devices, the respective gateway layer on top of the device layer was formed, and every single partner that delivered such a solution in the center project used a dedicated gateway device, which was able to collect information and dispatch commands to the respective devices, from and to the respective devices. And of course, in order to be able to gather all the information of the different systems and devices in an interoperable manner and deliver an interface to the rest of the main center components that perform the different operations, the data were gathered in this interoperability layer and were forwarded to the final layer, which was segmented to the consumer aspect and to the aggregator aspect. The consumer aspect contained the end user applications, and the aggregator aspect contained the flexibility profiling that generated the load shiftings necessary for the grid stability demanded by DSOs and aggregators. There were also some components that were relevant also to the consumer as well as to the aggregator, such as the EV charging management systems, the hot water, the smart hot water solutions, and the other energy management systems that provided within Sender. Now, we will focus on the modules that were suitable for the flexibility profiling. So we begin with hypertext and flexibility profiling framework, which included 3 subcomponents. The first one, it was a building as a battery component, which generally utilizes buildings as thermal batteries in order to store and manage energy efficiently. It extracts flexibility and reduces energy costs by shifting or setting thermal appliance power demands. This was realized through the implementation of a gray box thermal model, which relies exclusively on IoT metering and sensing data. And that's very important in order to design the thermal potential of its building with minimal data collection. And of course, we have the dedicated machine learning based models that helped us predict day ahead consumptions for the HVAC systems. The other 2 components that were included in the hypertext demand flexibility profiling framework was the comfort profiling module, which generally prioritizes thermal comfort profiling as thermal appliances are key flexibility contributors. This component helped us identify occupants' comfort boundaries based exclusively on sensing and monitoring data, relying on the multi-sensors, enabling the extraction of various comfort profiles per prosumer and per building space. Also, it ensured that the comfort profiles remain intact during the overall flexibility forecasting and dispatching, and that way it prevents the degradation of the living conditions in order to help the tenants maintain the demand response acceptance. Finally, the main component of the framework is the demand flexibility profiler, which delivers forecasts on a daily basis for demand flexibility from building appliances, and also provides day-ahead baselines and flexibility estimates for the controllable and DR-related appliances to be forecasted daily, to be updated, daily. And finally, it is designed to support aggregator platform operation by dispatching forecasted flexibility upon request. And to summarize the framework's aim, first of all, we have to extract the comfort profiles to able to realize which are the indoor conditions preferable by the tenants. Then, utilizing the building as a battery module, we were able to generate the baseline consumptions for the day-ahead forecasts based on the day-ahead forecast, which are basically the expected consumption for the day ahead according to the historic data of its tenant, of its user. And of course, the demand flexibility profiler delivered the modified consumption, the optimized consumption, the load shifted consumption, and subtracting this time series from the baseline consumption, we could deliver an evaluation and a measurement for the flexibility provided. So, Estibalis, I will pass the floor to you in order to describe your for us. Thank you very much.
Thank you.
I will trigger me and I will change the slides. Okay.
The slides, yeah.
Let's jump into the first. Thank you very much.
Okay, thank you. Well, hello again to you. Just a short introduction. I'm Estibalis from Trialog. And what we have provided here, and what I want to explain just briefly, is about the Senders EVC EMC, which is the electrical vehicle charging energy management system, which is best known right now as TROCA. We have renamed it, you can say commercially. Okay. So it is a software-based solution, a technical enable for electrical vehicle charging and load control services for the charging station sessions. Okay, it depends on many also constraints things outside external factors, but we provide flexibility to the grid, dynamic type schedule. It also can have exchanges with a different ecosystem of the electrical vehicle charging ecosystem, redundantly, we can say, with flexibility aggregator, the DSO, we provide flexibility. Just generally speaking, we can go to the next slide so I can explain a bit better. TROCA was conceived with a modular structure. This modular structure, which is allows an easier integration. It facilitates to be the adaptability to the different environments. We say different charging stations characteristics, needs or pilots, or okay. So this adaptability, this versatility, we can say, it is provided because each module is independent. It uses a different interface. So, for example, here in Sender, we didn't use all the modules you can see here. And I will just talk a bit about the main ones, such as the battery, we have the input of the ESS, the energy storage system, an output the schedule, the PV modules, so we can have the input of the PVs, the photovoltaic panels, And we can use it for the EV charging. The model grid, we have the grid power maximum input and the grid power schedule. One of the important ones is the flexibility module. But we have the input flexibility activation, and the output is the flexibility offer that we can provide to DSO, for example. And the last one, the EVSE, EV user. It uses the input of the limit power of the charging point, the departure time, and then we have as an output the different schedule of the EVSE. We can go to the next slide. I think, yeah, here we have some, we can see the, yeah, this one, yes. Well, you can see the name Troca Trailer Connectivity Asset right now, they changed. It depends on, well, it's a technical enable, okay, that can optimize the power consumption. It can execute in parallel or replace the charging station supervisor, and it has been also tested widely in different real existing charging stations. It depends also, as I have already said, in external constraints, depending on the renewable energy sources, because we have the model PV, the storage battery, and also that we already know the grid constraints and flexibility. We are right now preparing the Troca system for the next generation of vehicle to grid. Yes, and here I would like just to give you an overview of three main use cases that the system has already been tested positively in different projects, such as limitation of the day consumption through the PVs. We did this maximizing the EV charging using the PV, minimization of grid consumption with PV, battery, and electrical vehicle. How we charge firstly the battery with the PV input, and then we maximize the EV charging using not only the battery but also the PV. Okay, so both, we can say, through both modules. And of course, about the grid congestion, which is important. Here it comes again, the flexibility in the EV charging for DSO. I don't know if there's another one. Okay.
Okay.
Yeah. We will come.
You'll have the chance to revise
Yes.
add this more information on the next section of the presentation. Now, I would like to refer to the simulation and laboratory validation of the sensor solution provided by AIT. And Jawad, I pass the floor to you. And please let me know when you want to change the slides in order to have a smooth presentation from your side. Let's begin.
Okay, thank you, Thomas. Good afternoon, everyone. I think you will all agree, and this can be widely observed, that modern information systems are becoming more complex and interconnected, and it's no longer possible to design them using what is called the monolithic approaches. What we need is to adopt to more modular, loosely coupled, and system of systems approaches, because they provide required flexibility that is needed, which is not inherent in the monolithic systems. You would also agree that whenever we make some design changes, there are always trade-offs between them, and in this case, there is no exception. When we adopt to more modular approaches, on one hand, these approaches solve the problem because they can contain the complexity of the design by following what is called the separation of concerns, or in some other words, the abstraction effect. But on the other hand, they introduce more challenges, like it is now more required that individual components of the subsystem should be tested to validate whether they work together as a coherent system. Since Thomas already introduced the sender architecture a few slides ago, and you saw that the approach that we adopted in sender is also similar to a system of systems approach. where individual components are identified, modules are identified, and then they are developed by various partners to perform various functions. Now, as I mentioned earlier, in this case, it is necessary that we should have a thorough testing of the developed solution to ensure that the solution is interoperable, functionally aligned with the requirements, and also works seamlessly with the internal and external systems. To cover this aspect, in the next few slides, I will present a summary that covers the testing efforts that were done to test the sender solution. And as you can see on this slide, this slide tries to summarize the three core functions or three core phases of the tests that were conducted. These tests were developed a bottom-up approach. So first of all, we focused more on the intra-sender solution. So how the components inside consisting of the sender solution would need to be tested for their compliance and for their data exchange capabilities. Once this is done, we focused on how the sender solution would work with the accompanying external systems and how the data exchange protocol and communication standards will play and can be verified. And lastly, the functionality, like why the sender solution was developed. The answer is to enable next generation demand response. So the third phase was to see how this functionality can be enabled and tested with the developed solution. Next slide, please.
Of course.
So every good test methodology requires a plan and also a documentation. So we adopted the EU's Joint Research Council's Joint Research Center's interoperability testing methodology, which talks about defining application profiles and interoperability profiles. And this is a screenshot of this modified approach. So the idea is that we first identified interfaces that are interesting, the automation interfaces that are frequently used for the intercommunication. And then we also identified the data providers and data receivers. So this in total summarized to 11 these points, 11 these interfaces. And then for each of the defined interface, identified interface, a complete documentation was also filled out, which highlighted what this interface is about, what is the expected input and what is the expected output, and where this interface is playing a role in the overall sender's bigger picture. So keeping this documentation and this test setup in mind, the next slide tries to cover the testing framework. So of course we need a hardware in the loop controller, hardware in the loop testing approach, because maybe another factor to highlight here is that all these tests were conducted geographically in separate locations, like in the case of Hypertech and Trialog. The components were running on their site, and the simulation setup was running at AIT's site. So they were like not physically present in our lab, for example, in some cases like we do. But in this case, it was more like a geographically dispersed simulation setup. So talking about the setup itself, so you see in the middle, the VLab Central. VLab, by the way, is a framework that AIT provides. It's an interoperability by design framework that not only covers the validation and verification aspect, but also helps in designing and transferring the requirements into implementable artifacts, and also covers the scalability and replicability effects. So in this case, you see VLab Central is the computational hub that provides the services. In this case, you see the services like the Docker repositories, Kubernetes, some other computational efforts, virtual machines, and on top of that, since AIT is simulating the role of an aggregator, so the setup is for the OpenADR compliant validation environment, and OpenADR was simulated in two models, the pull mode and the push mode. For some of you who are familiar with OpenADR, they know that the OpenADR distinguishes between the virtual top node, which is usually the server, and the virtual end node, which is usually the client. So in this case, sender solution is as the virtual end node client, and virtual top node is the server. And the pull mode, in the pull mode case, that it is the client's responsibility to periodically check for the set points from the server. And in the push mode, the OpenADR server does the job. So whenever there is a new command, a new set point for a specific client, the server sends this to the client. So this is the overview of the setup. And this setup is, of course, based on the use case that Estebalis mentioned in a couple of slides ago. So next slide. So following this testbed setup, maybe one example that is interesting. So you saw Trialog's electric vehicle charging energy management system. And in this case, simulation or testing of this this case is highlighted. So the setting is that the EVC EMS is connected to a forecasting module, and it controls various charging points. And this there is an aggregator, which in this case AIT setup. So this aggregator is monitoring the grid, and whenever the aggregator sees that the grid needs some flexibility, it requests this flexibility from the EVC EMS, and EVC EMS sends the forecast to the grid to the aggregator, and based on the forecast and grid state, the aggregator calculates the set points and send it back to EVC EMS, and then EVC EMS distribute these set points to their respective charging infrastructures, the electric vehicle charging infrastructures. Next slide, please. This is a graphical depiction of the setup that I described. So at the AIT site, the VLab Central, the computational platform, is running virtual top node server like OpenADR pull mode aggregators simulator, which is also running a grid emulation, which is in the Panda Power. And on the Trialog side, they are running the virtual end node as the OpenADR client, which is also connected to a flexibility forecast and EVC EMS. And then EVC EMS is also connected to some infrastructure, electric vehicle infrastructure. The aggregator, the request is pulled from the EVC EMS, and respectively, it sends the flexibility forecast to the OpenADR server, and then OpenADR server sends back the set points for the respective charging points. Yeah, so this is the brief description of the setup. Maybe next slide. And now some results. So the upper graph shows the simulation result when the setup is run without any aggregate, like without the simulation of the EVC EMS and the aggregator. And as you can see, there are a lot of violations in this case. But the next graph shows when the same setup is run with the coordinated aggregator and the sender solution involvement in the DER scheme. Yeah, next slide. To summarize, there were in total 11 interoperability profiles or interoperability test setups. These 11 interoperability test setups were combined with 2 integration setups, as I described, because the aggregator could run either in the pull mode or the push mode. So these 11 interoperability test setups can be combined with these 2 integration scenarios. And then again, on top of that, 2 functional testing setups, like one for the electric vehicle by Trialog and the other for the building profile from the Hypertech can be combined to that. Overall, there were several iterations required and a lot of tests were conducted, but overall, most of the tests were successful. And there were some findings also from these setups that are documented, for example, in the project deliverable. If you are interested to know about these findings, you could look up at the public deliverables, or you can, if you have a specific question, you can ask us during this seminar, or it's also possible to send us an email if if you still like to know some more details. Yeah, I think that's it. A very high level summary of how the tests were conducted in the sender solution testing. And now back to you, Thomas.
Thank you very much, Jawad. That was very informative. Okay, now at this section of today's presentation, we will jump to the senders market and its overall technological breakthrough. So we will focus into the hardware aspect of the solutions, but not limited to hardware components. So depicting what Jawad described, and we had under the Sender project 3 different flexibility provision modules, one from Hypertech, one from Trialog, and one from NXTech. And along with some third-party APIs, for example, weather APIs, we managed to merge all this information into a common repository in which a partner had access to calculate the corresponding performance metrics. Now, beginning with the Hypertech Smartbox and IML Cloud solution, this end-to-end solution addressed the data extraction, the deployment of the devices, and the information flow to other system components. And to be more precise, the first step of capturing information from the actual sender pilots was to identify the existing systems and the topologies per household. So the first step of the procedure was the auditing process, in which we gathered specific information about each household and the appliances existing in each household. And so for that reason, we needed to, after identifying the appliances, to select the appropriate devices readily available from the market as well, in order to be able to find these devices and to deploy them. And each appliance had to match a different device for actuating and monitoring. For example, In underfloor systems, we needed smart thermostats depicted here. In AC split units, we needed IR controllers for the remote control. And beyond the actuation, the metering of such appliances, the metering of the total consumption and some metering of such appliances also demanded an extensive research on the circuit boards of each household in order to identify specificities and select the appropriate devices to capture the consumptions. For example, we had single-phase loads or third-phase loads in different households. Of course, the ambient conditions, the capturing of ambient conditions was much more straightforward, as some specific sensors were utilized in order to measure the indoor conditions, such as the air temperature, the relative humidity, luminance, and the occupancy. So after we identified the selected devices, after the selected devices were actually procured, we needed to install and commission all the IoT equipment in each of the households. So very many different professionals coordinated in this process in order to order the devices, and send representatives to each of the households, send the electricians to perform the installations on the circuit boards, and along with the IoT deployment in each and every household that implemented HyperTech solution, a smart box, dedicated smart box, accompanied the installation of the IoT devices. This smart box is basically a small computer that a Raspberry-based solution mainly that is able to communicate with the deployed IoT devices through different protocols such as Wi-Fi, such as Bluetooth or Z-Waves, and by communicating with the IoT devices, it is able to gather the data from the measurements for the metering metrics and the ambient condition metrics, and also is able to dispatch the control commands bidirectionally. So each of the household had its dedicated smart box, and the entirety of extract information from the households and the smart box specifically were gathered through Wi-Fi or Ethernet connections, and they were guided through the internet to a cloud-based infrastructure, the information management layer, which was basically a cloud repository and with some functionalities, extra functionalities regarding modification and cleansing of the datasets, with the sole focus to gather centrally this the entirety of information from all the smart books and make it available to other sender software modules, such as the demand flexibility profiling framework mentioned earlier, in order to be able to perform the calculations and other operations of the sender solutions. Now, Sibalis, can you share a couple of thoughts on your component in terms of interoperability? Thank you.
Thank you. Yes, here we can see well the structure with the different modules, and what we provide about interoperability. What I would like to say is you can see here the different protocols. We use the OCPP for communication 1.6 and also OCPP 2.0.1. We have also through the OpenADR the IEC 63382 for the Flex software. You will communicate through the aggregator, the OCP 211. So we provide really standardized protocols in our system. Also we have the interoperability with the smart grid actors. Why? Because we have adapted to SAREF and also to the Flex offer, as you can see here in different standards. That was one point I wanted to show you here. And just about the integration of TROCA, it's easier at EVC EMS. You can call it TROCA, it's easier, I would say. How we integrate the system. We can do it through the cloud directly to the charge point. Through the cloud with a proxy, and at the charge point, direct connection to charge points supervisor. In our case, we have everything through the cloud. We have done this in this project in Sender. And that's it.
Thank you very much. Thank you very much, Stybalis. Okay, I will mention a couple of words about the smart water heater provided by NXT. This solution is able to transform a standard water heater into a smart one by enabling great customization for diverse household needs. This cloud connection provides easy access and also includes a UI which allows for monitoring the water heater's electricity consumption and water filling level in real time or historically, and as well as enable the control and optimization of electricity and water consumption in households. Users gained access to very detailed and long list of settings and could decide on every aspect of boiler's functionality. We are using the water heater as a thermal battery, as an analog to what mentioned earlier for the EV and the building as a battery. It was made possible to delay heating and allow households to take advantage of lower electricity prices or power generated from the photovoltaic systems, and all this without compromising any of the occupants' comfort. So, the solution allows the user to control the heater both with a control panel on the boiler, directly on the boiler, or through the My Uplink mobile application, or through the internet browser URL. The connection with the device is considered plug and play, relatively easy, by scanning the QR code with the application in order to get data and control at once. The boiler has two heating elements and allows to use one or both, or completely to use one or completely both turn off the power. And the API was also allowing other settings such as vacation settings when the occupants are at the house for the summer period, for example, some boost modes for faster water heating, overheating if needed, leakage stop, and even some health aspects like the bacteria prevention of which occurs many times in water tank storages. The quality of the boiler's functionality and the user's experience was greatly improved through the solution. And for the Sender project, it was implemented open control of the boilers for both pilot partners and the users, and also providing an overview of the current state of the boiler in the Sender app, which will be mentioned later. Part of the Sender's households were using the price setting of the boiler, which ultimately is matching the boiler operation and heating the water in hours during hours of the day with the cheapest electricity prices, depicted in the graph in the middle. But also other part of the house, other households has used the scheduling mode of the boiler to be able to utilize their PV generation system power to heat the boiler. With that setting, they usually follow the data from solar panels to decide when it is the most beneficial to heat the water. Based on the data and the user feedback, users appear to prefer mostly heating time 4 to 6 hours to the day, and the preferable temperatures corresponded to 55 to 60 degrees. That's from my side for the smart water heater, and the next part of the presentation concerns the Sender's mobile application, and I will pass the floor to Antonis Stratis from Q Technologies to share his insights on the development of the mobile application. Please, Antonis.
Thank you, Thanos. Hi, everyone. I'm John Stratis from Q Technologies, and today we're going to demonstrate to you the Sender mobile application. The Sender mobile app was designed and developed in order to engage users to actively participate in the project by controlling their building assets, like the NXT boilers and hypertext solutions for domestic hot water appliances and HVAC systems. Additionally, the app allows the user to monitor their building ambient conditions, such as temperature and humidity, and also their energy consumption patterns. Since we created an intuitive user interface, we believe the best way to showcase our solution is through a demonstration video. So please, Thanos, if you could go to the next slide. Before proceeding, I would like to mention that the user, in order to access their virtual user, they need to enter their credentials. So please, Thanos, proceed.
Of course.
Upon login, the main screen is divided into two sections, favorite and groups. And the user can filter their appliances based on various criteria, like room or device name. They can also switch devices on and off with a single click. And on the other hand, the user can group multiple systems together, allowing them to control them with a click of a button. The default groups within the app are the rooms of the house, for example, here the living room. And if an IoT device loses connectivity, it is displayed with an exclamation mark to alert the user. Now, in this pop-up window, the user are able to adjust the fan speed, the mode of the AC unit, as well as the temperature set point. And also modify, if they want, the name of the device, of the system. Finally, the app offers an overview of the premise, including the energy that was consumed within 24 hours, the temperature, and the humidity. As well, there are graphs displaying the consumption over daily, weekly, and monthly periods. Also, we would like to demonstrate the Sender app through another video with a real-time demonstration. Please, Thanos, proceed. Here, the user enters their credentials, as we mentioned before, and also the Sender app provides the ability to change the language in order to be more user-friendly. As you may see, here we have a closed AC, and with a click of a button, we can activate it. And also adjust the temperature set point. That's also the overview that we mentioned before with the graphs. Thank you, everyone.
Thank you very much, Antonis, for your presentation and the nice video.
Thank you.
And okay, so that concludes the second section of technological breakthrough and the Sender's Toolkit. And we can jump to the final section of today's presentation, which concerns the data management and security in smart energy systems. Trilog has undertook this process and coordinated the overall management and security. So please, Sbalis, once again, I pass the floor to you, and you can share your thoughts. And I believe that there are some animations in the next slide. So I would try to support
Yes,
you.
okay. I think that as I talk, you can click on it. Okay.
Okay.
Okay. So, well, first of all, I would like just to give you an overview as maybe if we remind a slide that has been presented by Thanos with the architecture, we have like different layers from the systems, devices, communications, services, applications. So how do we deal with the security and privacy with the different systems, different services and applications and different partners? Okay, this is because I will explain later on the ecosystem view. We have followed a methodology, security and privacy plan, which is based on the ISO 27570 privacy guidelines for smart cities. This way I tell because here it has like 5 main processes for us, 5 main plans within the plan. Okay, it is an ongoing and dynamic plan. I mean, you can change the plan as a different list of actions that you have to plan to do it. Okay, and we have applied the plan. First, we have defined the plan with different actions we have to do in the different these 5 governance, data management, risk management, energy and engineering management, and citizen engagement. If you click a bit, okay. The governance management plan here will limit first the governance body who is going to work on it, who is going to handle with the security and privacy within the pilots, partners, representative with the different systems, and the framework, the legislation framework, and also could be also a standardization framework to limit. Okay, in our case, we skipped the new legislation right now that entered into force, the AI Act, because Sender is finishing right now this month. But if not, we should have also taken into account and make more, we can say, risk management about it. But okay, the point is to limit that legislation. Then the part of the data management. Here we can talk about the data lifecycle because we have been collecting data from users within 1 year. Okay, so how do we deal with this? With it, we have to be compliant with the law. We have also to be careful with the PIIs, is the personal information, personal data, how we share data within the consortium, the partners, even if it's necessary with third parties. So we can use agreements, joint data controller agreements with it, or could be also between controllers and processors agreements. How to monitor this, the data, the exchange, data flow diagrams, everything of this. Okay, this is part of the plan. The next part of the plan is the risk management plan. Here, first, we discuss about the context. Do we need to do security risk management, privacy impact assessment? So all these kind of things about the context and what are we going to do? What we are going to do a security risk assessment and privacy risk assessment. Okay, through different methodologies, we plan in we list these actions in the risk management plan. Then we have also the part of the engineering management plan, which is about the privacy by design. The main, we can say, standard. We have the 27550. It's about privacy engineering. It's like to integrate privacy requirements and privacy strategy is oriented to data sharing, to data protection within the deployment, the development and implementation, even also, of course, the design of the systems of the Sender architecture. And lastly, the citizen engagement. Well, here I think there has been another webinar about consumer engagement, deal with all these kind of things that interwoven a bit also with the security and privacy plan. You have to be taking into account the consents. If you need, we have done also privacy notice, different agreements, internal ones, maybe also with consumers, and also engagement and strategies. Okay, so it interweaves a bit with other parts of the project. Okay, if we go to the next slide, I just focus here a bit about the data management plan, what we did. Okay, we have to identify which is the data controllers, the individuals, processors, who is the owner of the data. Here in the process, as I have already said, we had an agreement, joint controllers agreement. It was the best option for us. You have to be careful how you are sharing the data between not only the different partners, even also if you have third parties included for another kind of analysis or services out of the project. Here in the data management, we take into account the data description, which is the life cycle of the data also, which is very important to really inform to the users type of data. We are going to storage this, how much time, date of collection, date of deletion, for what purpose, very explicitly, all these kind of things, and specify the exchange of the data flow diagrams, access control, monitoring, and have a registry of the data with contents, agreements, data sets, all these kind of things, how to manage. And just as a summary, we can say that this kind of ecosystem view I have said before at the beginning, this is because as you have seen in the architecture system picture of Sender, we have different systems, different layers. It is not only one system of interest. They are interacting between them. We have different actors, users in different pilots. So how do we manage this? That's why I have been saying about this ecosystem point of view. We deal with this because we need to know that when you have different system of systems, there are new risks, emerging new risks. So you have to be taking into account everything. This is why we did privacy and security risk analysis, not only at the pilot sites, okay, each per pilot, but also through the different main systems. The IoT supervision package, hybrid system, EVC, EMC, EMS, sorry, TROCA, I think it's easier, okay, and also the hot water tank system. So with these capabilities, we can use to build for the Sender apps and services, if it's needed also, more to be accurate with security requirements or privacy. And then we did the pilot in Finland, Austria, and Spain risk assessment, okay, about privacy and security. So we will the capabilities on security and privacy from the bottom to the top with an ecosystem view to have everything to account, because the different systems, you can have new risks, okay. And just to finish is that this plan, it's something that is ongoing and dynamic. I mean, you can continue following and improving and check the analysis you have already done, the different controls, measures, etc., and also beyond the project if it's needed, of course. And that's how we handle in the vision of data management and security and privacy within Sender architecture.
Okay, thank you very much, Stybalis, for your final presentation. Okay, we have a dedicated question and answer session for the participants. So please, might you have any question on the presentation? Please feel free to ask them at this point of the presentation. I'm leaving the sharing on, and do we have something from the chat, something from the participants? Do you need some clarifications? I understand that there were, so it was a very technologically heavy presentation. We mentioned all the technical aspects and the very many interactions that needed to be performed in a secure manner, adhering to protocols, adhering to standards. And I believe that three widely different modules, hypertext modules, AI, NXT modules, and Trialogs module, we managed to perform this interoperable framework that allowed for the information flow from the appliance to the end user. That's my final remark on this presentation. I don't know if there are any questions to be addressed. Thank you. Peter wants to ask something, I guess. Thank you, Dieter. I guess that we were very detailed in our presentation explanation, so this didn't trigger any questions eventually. Okay. I don't know if any of the partners that participated, they have any remark to make, or maybe a constraint that they face. This is something significant. For my side, maybe to trigger a minor discussion. As I mentioned, at least for hypertext part, but I'm pretty sure that same goes for the NXT and Trilog. The procedure of finding the suitable prosumers with suitable appliances, the controllable loads, and thinking that we had to face legacy systems many times, at least for hypertext solution. This was a very demanding procedure that involved many different professionals, and the coordination of these teams were it was a very difficult task to perform, and there was so much back and forth, especially in the pilots. The pilot partners showed tremendous efforts to coordinate the installations, the procurements, the commission. They dedicated resources for on-site visits. From hypertext part, at least we had online support, and we tried to remotely address as many problems as we could. So we dedicated many resources for that manner as well. And finally, I believe that the envision of the sender vision was materialized in a satisfying way, along with the constraints and the barriers and everything that made it difficult to us. I believe we overcame that, and we have a robust framework. The sender framework is robust, has many things to deliver, has many feedback, significant feedback, and on the installation, on the data, and stuff like that. The public deliverables will conclude, I think, right now on March 31st of March. So if any of the participants would like to check on these public documents and has specific questions regarding installations, regarding data analysis, regarding data management, feel free to contact us. And personally, I have no other remarks to make. And if there are no questions, we could conclude our today's webinar.
Thanks a lot.
Thank you very, very much. Thank you very much, everyone.
Okay. Bye-bye.
Okay.
Thank you. Bye.
Bye. Thank you for participating.
Thank you. Bye-bye.
Bye-bye. Bye-bye.